Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the puzzling story of Three-Eye Atlas, a cosmic visitor whose unexpected movements challenged our understanding of celestial mechanics and revealed the hidden forces that shape the journeys of interstellar wanderers. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined, a long thank you. In the quiet hours before dawn on October 15th, 2019, automated telescopes tracking 3 Atlas detected the first hint that this interstellar visitor was not behaving according to the elegant mathematical predictions of celestial mechanics. The comet's position against the star field had shifted by amounts that exceeded the measurement uncertainties, indicating trajectory changes that could not be explained by the gravitational influence of the Sun, planets, and moons alone. These subtle deviations from predicted orbital motion represented the first evidence that forces beyond pure Newtonian gravity were acting upon this ancient wanderer from another stellar system. Astrometric measurements precise to milliarc seconds revealed systematic position errors that accumulated over weeks of observation, creating a pattern of orbital deviation that suggested acceleration in directions that did not align with the gravitational field vectors calculated from planetary ephemerides. The magnitude of these positional anomalies measured only a few kilometers in the comet's actual location compared to theoretical predictions. Yet these tiny discrepancies represented forces powerful enough to alter the trajectory of a 2-kilometer-wide object traveling at interstellar velocities. The discovery of non-gravitational forces affecting Three-Eye Atlas followed a long tradition of astronomical puzzles where celestial objects refused to conform to theoretical expectations. Historical precedents included Halley's Comet, arriving weeks late for its predicted 1758 return, Neptune's gravitational influence being detected through Uranus's orbital perturbations, and the gradual recognition that comets experience rocket-like forces from sublimating gases that create thrust effects measurable across astronomical distances. Initial attempts to explain the orbital anomalies focused on undetected mass concentrations within the solar system, hypothetical dark matter, clumps, undiscovered asteroids, or measurement errors in planetary masses that could create gravitational perturbations sufficient to account for the observed trajectory changes. However, systematic analysis of these possibilities revealed that no reasonable distribution of additional mass could produce the specific pattern of acceleration detected in Three-Eye Atlas's motion without simultaneously affecting other solar system objects in ways that contradicted decades of precise planetary observations. The mystery deepened as continued observations revealed that the non-gravitational accelerations were not constant, but varied systematically with the comet's distance from the Sun, suggesting that solar heating or radiation effects contributed to the anomalous forces. This distance-dependent behavior ruled out most gravitational explanations and pointed toward physical processes operating on or within the comet's nucleus that responded to changing solar radiation intensity as the object approached perihelion. Only took a few weeks of precise astrometry to overturn centuries of confidence in pure gravitational mechanics for predicting comet trajectories. The realization that interstellar visitors might behave according to different physical principles than solar system objects challenged fundamental assumptions about the universality of celestial mechanics and highlighted the limitations of theoretical models developed exclusively from observations of gravitationally bound solar system bodies. Radio astronomy techniques contributed additional constraints on the anomalous motion through precise Doppler measurements of the comet's radial velocity, revealing acceleration components that could not be detected through optical position measurements alone. These radar observations provided three-dimensional velocity vectors that confirmed the reality of non-gravitational forces while ruling out systematic errors in optical astrometry that might have created false acceleration signals. The precision required for detecting these subtle orbital deviations pushed astronomical measurement techniques to their absolute limits, requiring coordination between multiple observatories and sophisticated statistical analysis to separate genuine trajectory changes from the accumulated uncertainties of individual position measurements. Each observation represented a single data point in a complex dynamical puzzle that required months of careful analysis to distinguish signal from noise in the orbital solution. Theoretical orbital mechanics calculations revealed that the detected non-gravitational accelerations, though small in absolute terms, would accumulate over the comet's multi-year passage through the solar system to produce trajectory changes measuring thousands of kilometers by the time 3I Atlas departed into interstellar space. These cumulative effects demonstrated that even tiny forces could significantly alter the future destinations of interstellar wanderers during their brief encounters with stellar systems. The search for explanations of the anomalous motion required consideration of physical processes that operate negligibly on typical solar system objects, but could become significant for bodies with the unusual composition, structure, and thermal properties characteristic of interstellar visitors. The alien nature of 3I Atlas's formation environment around a distant massive star had created a cosmic object whose response to solar system conditions differed fundamentally from the behavior of local comets and asteroids. Comparative analysis with the previously detected interstellar object Oumuamua revealed similar patterns of non-gravitational acceleration, suggesting that anomalous motion might represent a common characteristic of interstellar visitors rather than a unique property of 3I Atlas. This comparative evidence indicated that the physical processes responsible for trajectory deviations operated universally on objects originating beyond the solar system, regardless of their specific composition or formation history. The implications of non-gravitational forces affecting interstellar objects extended beyond purely academic questions of celestial mechanics to encompass practical concerns about predicting the future trajectories of cosmic visitors and assessing potential impact risks from objects whose orbital evolution could not be accurately forecast using conventional gravitational models. Each detected interstellar visitor required individual analysis of its unique dynamical behavior rather than relying on standardized orbital prediction algorithms. Computer simulations of 3I Atlas's long-term orbital evolution revealed that the non-gravitational accelerations would continue affecting its trajectory long after departing the solar system, creating uncertainty regions that expanded over time to encompass vast volumes of interstellar space. These trajectory uncertainties made it impossible to predict which stellar systems the comet might encounter during its future wandering, transforming precise orbital mechanics into probabilistic estimates of cosmic destinations. The anomalous motion of 3I Atlas represented more than a technical curiosity in orbital mechanics. It revealed fundamental gaps in understanding the physical processes that govern the behavior of matter formed in alien stellar environments when subjected to the radiation and gravitational fields of foreign stellar systems. Each unexplained acceleration component provided clues about the exotic physics operating within materials that had never previously encountered solar system conditions. The careful accumulation of astrometric data over months of observation revealed that 3I Atlas was experiencing systematic velocity changes that defied explanation through any known gravitational mechanism, with acceleration vectors pointing in directions that bore no relationship to the gravitational field gradients created by solar system masses. Precise Doppler radar measurements detected velocity shifts measuring several centimeters per second, tiny by human standards, yet representing forces capable of deflecting a kilometer-sized object from its predicted trajectory by thousands of kilometers over the course of its solar system passage. These non-gravitational accelerations exhibited patterns that correlated with the comet's distance from the Sun, reaching maximum intensity during closest approach and diminishing systematically as the object receded toward the outer solar system. The inverse relationship between acceleration magnitude and solar distance suggested that electromagnetic radiation or particle bombardment from the Sun provided the energy source driving the anomalous motion. Yet the specific mechanisms remained elusive despite intensive theoretical investigation. Vector analysis of the acceleration components revealed forces acting predominantly in the anti-sunward direction, creating a net outward push that increased the comet's orbital energy and extended its hyperbolic trajectory beyond the values predicted by pure gravitational mechanics. This radial acceleration pattern resembled the radiation pressure effects that influence the motion of dust particles and solar sail spacecraft. Yet the magnitude exceeded theoretical predictions for radiation pressure on a solid nucleus by factors of hundreds. The discovery that non-gravitational forces could significantly alter the trajectories of interstellar objects challenged fundamental assumptions about the predictability of cosmic visitor orbits and highlighted the limitations of orbital determination methods developed exclusively for gravitationally bound solar system bodies. Traditional orbital mechanics relied on the principle that gravitational forces alone determined celestial motion, yet 3I Atlas demonstrated that additional physics became important for objects with compositions and structures unlike those found in the local planetary environment. Laboratory measurements of momentum transfer during photon absorption and emission revealed that electromagnetic radiation carries sufficient energy to accelerate massive objects through direct momentum exchange, with the effectiveness depending critically on the surface properties, composition, and geometric shape of the target body. However, standard radiation pressure calculations for rocky or icy surfaces predicted acceleration magnitudes far smaller than those observed in 3I Atlas's motion, indicating that exotic surface properties or internal processes amplified the momentum transfer beyond conventional expectations. Only took electromagnetic radiation a few minutes to travel from the Sun's surface to 3I Atlas's nucleus. Yet the acceleration effects accumulated continuously over months of solar exposure to create trajectory changes that would influence the comet's motion for millions of years during its subsequent interstellar wandering. The persistence of these acceleration effects demonstrated that even brief encounters with stellar radiation could permanently alter the cosmic trajectories of wandering bodies through momentum transfer processes operating over astronomical distances. Theoretical models of radiation pressure enhancement through surface roughness and porosity suggested that highly textured surfaces could create momentum multiplication effects, where incoming photons undergo multiple reflections and absorptions before escaping, effectively amplifying the momentum transfer compared to smooth surfaces. Computer simulations indicated that fractal surface structures with appropriate geometric properties could theoretically produce radiation pressure enhancements sufficient to account for 3I Atlas's anomalous acceleration. The mystery of enhanced momentum transfer found potential resolution through consideration of sublimation-driven mass loss that could create jet-like effects where escaping gas molecules carried away momentum in preferred directions, generating rocket-like thrust forces that supplemented direct radiation pressure. However, spectroscopic observations failed to detect the intense outgassing activity that would be necessary to produce momentum transfer rates comparable to the observed acceleration magnitudes. Magnetic field interactions provided alternative mechanisms for anomalous acceleration through electromagnetic forces acting on charged particles and electrically conducting materials within the comet's nucleus. Solar wind particles and cosmic rays could theoretically charge the object's surface to electric potentials sufficient to create electromagnetic forces when interacting with the solar magnetic field, producing acceleration effects that would vary with solar activity and interplanetary magnetic field orientation. Thermal expansion and contraction cycles driven by solar heating created additional possibilities for non-gravitational acceleration through mechanical processes that could eject material preferentially in specific directions or create internal stress patterns that altered the object's mass distribution and rotational dynamics. These thermomechanical effects could theoretically operate through mechanisms analogous to the thermal cycling that affects artificial satellites and creates orbit perturbations through differential thermal expansion. The search for acceleration mechanisms required consideration of physical processes that might operate differently on interstellar objects compared to solar system materials, including exotic ices with unusual sublimation properties, metallic phases with anomalous electromagnetic responses, or structural configurations that amplified solar radiation effects through resonance phenomena. Each potential mechanism required detailed theoretical analysis to determine whether it could produce accelerations of the observed magnitude and direction. Gravitational gradient effects across the finite size of 3I Atlas's nucleus created tidal forces that could theoretically contribute to trajectory perturbations. Yet calculations revealed that these differential gravitational effects produced accelerations orders of magnitude smaller than the observed anomalies. The failure of tidal explanations to account for the trajectory deviations eliminated purely gravitational mechanisms and confirmed that electromagnetic or mechanical processes must be responsible for the anomalous motion. Comparative analysis of acceleration patterns in different interstellar objects revealed systematic similarities that suggested common physical mechanisms operating on all cosmic visitors, regardless of their specific compositions or formation histories. This universality of non-gravitational effects indicated that the responsible physics represented fundamental aspects of electromagnetic or thermodynamic interactions, rather than exotic properties unique to individual objects. The implications of unexplained acceleration mechanisms extended beyond academic questions of celestial mechanics to practical concerns about planetary defense strategies for potentially hazardous interstellar objects whose trajectories could not be accurately predicted using conventional orbital mechanics. The inability to forecast precise impact probabilities for objects experiencing non-gravitational forces created significant uncertainties in risk assessment procedures for cosmic visitors. Computer modeling of long-term trajectory evolution under non-gravitational acceleration revealed that small force differences could lead to dramatically different cosmic destinations over millions of years of interstellar wandering, creating chaos-like sensitivity to initial conditions that made precise long-term orbital prediction impossible. These sensitivity effects transformed deterministic orbital mechanics into probabilistic trajectory forecasting for interstellar objects. Laboratory experiments designed to replicate the acceleration mechanisms proposed for 3I Atlas required sophisticated facilities capable of simulating the vacuum, radiation, and electromagnetic conditions of interstellar space while measuring minute force effects on test objects with compositions analogous to cosmic materials. These experimental approaches provided crucial tests of theoretical acceleration mechanisms under controlled conditions that isolated specific physical processes. The persistence of unexplained acceleration effects in multiple interstellar visitors suggested that current understanding of electromagnetic and thermodynamic processes in cosmic environments remained incomplete, highlighting fundamental gaps in knowledge about how matter formed in alien stellar systems responds to the radiation and gravitational fields encountered during passage through foreign planetary systems. The spectroscopic detection of asymmetric gas jets erupting from 3I Atlas's nucleus provided the first direct evidence for rocket-like thrust effects that could account for at least a portion of the comet's anomalous acceleration. As sublimating ices and organic compounds created preferential outgassing in directions that generated net momentum, transfer sufficient to alter the object's trajectory over time. High-resolution imaging revealed discrete active regions on the nucleus surface where solar heating had penetrated sufficiently to drive vigorous sublimation of subsurface volatile materials, creating collimated gas streams that carried away momentum in specific directions rather than the uniform spherical outgassing typical of solar system comets. These outgassing events exhibited temporal variations that correlated with the comet's rotation period, indicating that active regions moved in and out of direct solar illumination as the nucleus spun, creating pulsed thrust effects that varied systematically with the orientation of jet-producing areas relative to the incoming solar radiation. The resulting acceleration pattern created a complex interplay between rotational dynamics and translational motion that required sophisticated computer modeling to separate orbital perturbations from rotational effects. Mass spectrometric analysis of the outgassing plumes revealed molecular compositions dominated by water vapor, carbon monoxide, and carbon dioxide. Yet the abundance ratios differed significantly from typical solar system comets, suggesting that volatile inventories shaped by formation in alien stellar environments created sublimation behaviors unlike anything observed in local cometary bodies. The exotic ice compositions detected in 3I Atlas's outgassing included methane clathrates, ammonia hydrates, and organic polymers that sublimated at different temperatures and created complex multi-component gas flows. Thermal modeling of subsurface heat conduction revealed that solar radiation penetrated only the outermost few centimeters of the nucleus surface, yet vigorous outgassing occurred from depth that should have remained frozen, according to conventional thermal calculations. This apparent contradiction suggested either enhanced thermal conductivity through fracture networks that channeled heat into the interior, or exotic ice phases with sublimation properties that differed from standard water ice behavior under solar system conditions. The directionality of outgassing jets created torque effects that altered the comet's rotational state, causing changes in spin rate and orientation that were detectable through periodic variations in reflected sunlight and outgassing intensity. These spin-orbit coupling effects demonstrated that outgassing forces could influence both translational and rotational motion simultaneously, creating complex dynamical behaviors that required integrated analysis of orbital mechanics and attitude dynamics. Only took solar heating a few hours to penetrate sufficiently into the nucleus surface to trigger vigorous sublimation events. Yet the momentum accumulated through continuous outgassing over weeks and months of solar exposure created trajectory changes measuring thousands of kilometers by the time the comet completed its passage through the inner solar system. The cumulative effect of seemingly minor daily thrust increments demonstrated how small but persistent forces could produce major orbital perturbations over extended time periods. Computational fluid dynamic simulations of gas flow through porous nucleus materials revealed that subsurface pressure buildup could create sudden explosive release events when internal gas pressure exceeded the mechanical strength of overlying material layers. These sublimation explosions ejected both gas and solid particles in concentrated bursts that generated impulse-like thrust effects significantly stronger than steady-state outgassing from the same surface areas. The mystery of selective outgassing from specific nucleus regions found partial explanation through surface composition mapping that revealed heterogeneous distributions of volatile-rich and volatile-poor materials across the nucleus surface. Areas enriched in easily sublimated compounds became preferentially active under solar heating, while refractory-rich regions remained largely inactive, creating the observed asymmetric outgassing patterns that generated net thrust forces rather than balanced momentum exchange. Dust entrainment in outgassing flows created additional momentum transfer through solid particle ejection that supplemented the thrust effects of pure gas sublimation. With microscopic dust grains accelerated to velocities exceeding several hundred meters per second before escaping the nucleus gravitational field. The mass flux of entrained particles could theoretically contribute momentum transfer rates comparable to gas sublimation, effectively doubling the thrust efficiency of outgassing events. Subsurface cavity formation through continued sublimation created internal voids that could collapse suddenly and redirect gas flows towards surface fractures and vents, producing episodic outgassing events with thrust directions that changed unpredictably as internal structure evolved. These structural modifications meant that outgassing patterns observed during early solar approach might not persist throughout the comet's passage, creating temporal variations in thrust direction and magnitude. Crystalline phase transitions in exotic ices under solar heating provided additional mechanisms for sudden gas release events, where metastable ice phases underwent rapid transformation to more stable configurations, releasing trapped gases in explosive bursts that generated impulse-like thrust effects. Laboratory studies of similar phase transitions in nitrogen and carbon monoxide ices demonstrated that these processes could produce gas release rates exceeding steady sublimation by factors of hundreds. The efficiency of momentum transfer through outgassing depended critically on the escape velocity required for gas molecules to leave the nucleus gravitational field. With the small mass and weak gravity of 3I Atlas, allowing even slow-moving gas molecules to escape rather than falling back to the surface. This low escape velocity maximized the thrust efficiency of outgassing by ensuring that nearly all sublimated material contributed to momentum transfer rather than remaining gravitationally bound. Temperature gradients across the nucleus surface created differential sublimation rates that produce systematic thrust imbalances, with the warmest regions generating the strongest outgassing and creating preferential thrust in directions opposite to peak solar heating. These thermal asymmetries meant that outgassing thrust effects automatically aligned with anti-sunward directions, explaining the observed pattern of radial acceleration that increased the comet's orbital energy. Organic polymer sublimation contributed additional complexity to outgassing behaviors through molecular decomposition processes that could produce gas release at temperatures below the sublimation points of simple ices, extending the range of solar distances over which significant outgassing could occur. the decomposition of complex organic compounds detected in 3I Atlas created gas production that continued even at distances where water ice sublimation became negligible. Laboratory measurements of sublimation rates from analog materials under simulated solar heating conditions revealed that exotic ice compositions could produce gas release rates significantly higher than pure water ice, providing theoretical frameworks for understanding the enhanced outgassing efficiency required to generate the observed thrust effects. These experimental studies confirmed that alien ice compositions could create sublimation behaviors unlike those of typical solar system comets. The persistence of outgassing activity throughout 3I Atlas's solar passage created cumulative thrust effects that continued altering the trajectory long after peak solar heating, demonstrating that rocket-like forces could influence interstellar object motion over timescales extending far beyond brief perihelion passages. The long-duration nature of these thrust effects highlighted the importance of outgassing mechanisms for understanding the orbital evolution of cosmic visitors. The interaction between solar photons and 3I Atlas's surface materials created radiation pressure effects that exceeded theoretical predictions by margins that challenged conventional understanding of electromagnetic momentum transfer, suggesting that the comet's alien surface properties amplified photon interactions through mechanisms unknown to solar system materials. Precise photometry revealed that the object's light scattering behavior differed significantly from typical asteroids and comets, with phase function anomalies that indicated unusual surface textures or compositions that enhanced the absorption and re-emission of solar radiation in ways that maximized momentum transfer. Standard radiation pressure calculations assumed smooth, uniformly reflecting surfaces that absorbed and scattered incident photons, according to well-established optical principles. Yet spectroscopic observations revealed that 3I Atlas exhibited complex scattering behaviors suggesting surface structures that created multiple photon interactions before final escape. These enhanced interaction processes could theoretically multiply the momentum transfer per incident photon through cascading absorption and re-emission events that operated like microscopic photon pinball machines across the nucleus surface. Polarimetric measurements of reflected sunlight revealed systematic variations in polarization state that indicated surface textures with characteristic length scales comparable to optical wavelengths, creating interference effects that modified radiation pressure through resonant enhancement of electromagnetic field interactions. Laboratory studies of similar textured surfaces demonstrated that appropriately sized surface features could create standing wave patterns that concentrated electromagnetic energy and enhanced momentum transfer beyond flat surface predictions. The discovery of preferential radiation pressure in specific directions contradicted the assumption that electromagnetic forces should act radially outward from the Sun, indicating that surface asymmetries or internal electromagnetic properties created directional selectivity in photon momentum transfer. Computer simulations revealed that non-spherical shapes, heterogeneous surface compositions, or structured material interfaces could theoretically create radiation pressure imbalances sufficient to generate net thrust forces in preferred directions. Thermal infrared observations revealed that 3I Atlas absorbed solar radiation more efficiently than typical rocky surfaces, while simultaneously exhibiting enhanced thermal emission that suggested rapid heat redistribution through highly conductive internal structures. This thermal behavior created temperature gradients that drove thermophotonic effects, where thermal radiation carried away momentum in directions determined by surface temperature patterns rather than purely geometric considerations. Only took electromagnetic radiation 8 minutes to travel from the Sun's photosphere to 3I Atlas's nucleus. Yet the cumulative momentum transfer from billions of photon interactions over months of solar exposure created acceleration effects that would influence the comet's trajectory for millions of years during subsequent interstellar wandering. The patient accumulation of microscopic momentum increments demonstrated how electromagnetic forces could compete with gravitational effects over cosmic timescales and distances. Spectroscopic analysis of surface mineral compositions revealed unusual abundance patterns of metallic elements that could create electromagnetic resonance effects, where specific wavelengths of solar radiation interacted preferentially with electronic transitions in metallic phases, enhancing absorption cross-sections and momentum transfer rates for particular portions of the solar spectrum. These selective absorption processes could amplify radiation pressure effects while creating wavelength-dependent thrust variations. The mystery of enhanced radiation pressure found potential resolution through consideration of surface porosity effects, where photons could penetrate into subsurface cavities and undergo multiple scattering events before escaping, effectively increasing the path length of electromagnetic interactions and multiplying momentum transfer compared to solid surface reflections. Radar observations suggested that 3I Atlas possessed internal structure consistent with high porosity that could support such photon trapping mechanisms. Photonic crystal effects within crystalline surface materials provided alternative mechanisms for radiation pressure enhancement through coherent scattering processes that could focus or redirect electromagnetic energy in ways that concentrated momentum transfer in specific directions. Laboratory studies of similar crystalline materials demonstrated that periodic structures with appropriate lattice parameters could create photonic band gaps and enhancement regions that modified electromagnetic interactions. Electromagnetic field coupling between solar wind magnetic fields and electrically conducting materials within the nucleus created additional opportunities for enhanced momentum transfer through magnetodynamic effects that supplemented pure photon pressure. The solar wind carried embedded magnetic fields that could induce electric currents in conductive nucleus materials, creating electromagnetic forces that varied with solar wind conditions and magnetic field orientations. Surface charge accumulation through solar wind particle bombardment created electrostatic effects that could modify radiation pressure through Coulomb interactions between charged surface regions and the electromagnetic fields of incident photons. Plasma physics calculations revealed that surface charging could reach potentials sufficient to create measurable electromagnetic forces when interacting with the oscillating electric fields of solar radiation. Anisotropic thermal conductivity within the nucleus materials could create temperature asymmetries that produced preferential thermal radiation patterns, generating net momentum transfer through asymmetric photon emission rather than reflection or absorption. These thermal asymmetries meant that radiation pressure effects continued operating even when direct solar illumination was blocked, as stored thermal energy was released preferentially in specific directions. Quantum coherence effects in crystalline materials provided exotic mechanisms for enhanced electromagnetic interactions, where coherent photon absorption and emission processes could create constructive interference that amplified momentum transfer beyond classical predictions. These quantum enhancement effects required specific material properties and electromagnetic field conditions, but could theoretically produce radiation pressure amplification factors sufficient to explain the observed acceleration anomalies. Multi-wavelength observations revealed that radiation pressure effects varied systematically across different portions of the electromagnetic spectrum, with enhanced momentum transfer occurring preferentially in infrared wavelengths, where thermal emission dominated over reflected visible light. This wavelength selectivity suggested that thermal radiation processes contributed significantly to the total electromagnetic momentum transfer, supplementing direct solar radiation pressure. Laboratory experiments using intense laser beams to simulate solar radiation pressure on analog materials demonstrated that textured surfaces could indeed produce momentum transfer enhancement factors of 10 to 100 compared to smooth surfaces, confirming that surface structure modifications could theoretically account for the radiation pressure anomalies observed in 3I Atlas's motion. These experimental validations provided crucial support for enhanced electromagnetic interaction models. The persistence of radiation pressure effects throughout the comet's solar passage created continuous acceleration that accumulated over time to produce significant trajectory modifications, demonstrating that electromagnetic forces represented a fundamental aspect of interstellar object dynamics, rather than minor perturbations that could be safely neglected in orbital calculations. Each photon interaction contributed microscopic momentum increments that collectively produced measurable orbital changes over astronomical distances and timescales. The metallic components embedded throughout 3I Atlas's nucleus created unexpected opportunities for magnetic field interactions that generated electromagnetic forces capable of influencing the comet's trajectory through mechanisms analogous to the magnetic coupling between solar wind plasma and planetary magnetospheres. High-resolution magnetometry revealed that the object possessed a weak but detectable magnetic signature that varied systematically with its orientation relative to the interplanetary magnetic field, indicating that ferromagnetic materials within the nucleus responded to external magnetic forces in ways that could contribute to the observed orbital anomalies. Iron-nickel grains distributed throughout the comet's internal structure exhibited magnetic susceptibilities that created induced magnetic moments when exposed to the solar wind's embedded magnetic field, generating attractive and repulsive forces that varied with the strength and orientation of the local interplanetary magnetic environment. These electromagnetic interactions operated through the same physical principles that govern compass needle behavior in terrestrial magnetic fields, yet scaled up to cosmic dimensions where even weak magnetic forces could accumulate over time to produce measurable trajectory changes. Solar wind plasma streaming past 3I Atlas at velocities exceeding 400 km per second carried frozen-in magnetic field lines that created time-varying electromagnetic environments as the comet moved through different regions of interplanetary space characterized by varying magnetic field strengths and orientations. The dynamic nature of these magnetic interactions meant that electromagnetic forces fluctuated continuously as the object encountered magnetic field structures associated with solar wind streams, coronal mass ejections, and interplanetary current sheets. Paleomagnetism preserved within the comet's metallic grains provided evidence of exposure to intense magnetic fields during formation around a massive star whose magnetic environment exceeded solar field strengths by orders of magnitude, creating permanent magnetization patterns that could interact with contemporary magnetic fields encountered during solar system passage. These ancient magnetic signatures meant that 3I Atlas carried within its structure a magnetic memory of its alien birth environment that continued influencing its electromagnetic behavior. The discovery of magnetic torque effects acting on the comet's nucleus provided additional evidence for electromagnetic coupling between internal metallic components and external magnetic fields, with systematic variations in rotational motion that correlated with changes in interplanetary magnetic field orientation. These magnetic torques operated through the same mechanisms that control the attitude of Earth-orbiting satellites using magnetic torque rods, demonstrating that natural cosmic objects could experience similar electromagnetic control effects. Only took magnetic field interactions a few seconds to propagate through the comet's nucleus and establish electromagnetic coupling between metallic components and the surrounding solar wind plasma environment. Yet the cumulative effects of continuous magnetic forces over months of solar system passage created trajectory modifications that would persist throughout the object's subsequent interstellar wandering. The instantaneous nature of electromagnetic interactions contrasted with the gradual accumulation of their mechanical effects over astronomical timescales. Eddy current generation within electrically conducting materials created additional electromagnetic effects, where time-varying magnetic fields induced circular electric currents that produced opposing magnetic fields according to Lenz's law, creating electromagnetic drag forces that resisted changes in magnetic field exposure. These eddy current effects operated like electromagnetic brakes that could influence rotational dynamics and create coupling between magnetic field variations and mechanical motion. The mystery of magnetic field amplification within the comet's porous structure found potential explanation through magnetohydrodynamic effects, where solar wind plasma flow through the nucleus interior could stretch and concentrate magnetic field lines, creating local magnetic field enhancements that exceeded the ambient interplanetary field strength by significant factors. Computer simulations revealed that appropriate porosity and conductivity distributions could theoretically produce magnetic field amplification sufficient to generate measurable electromagnetic forces. Magnetic reconnection events between the comet's internal magnetic field and the interplanetary magnetic environment provided mechanisms for impulsive electromagnetic acceleration through sudden magnetic field line reconfiguration that release stored magnetic energy as kinetic energy of charged particles and bulk plasma motions. These reconnection processes operated on timescales of minutes to hours, yet could produce impulse-like force effects that contributed to orbital perturbations. Plasma wake formation behind 3I Atlas, as it moved through the solar wind, created electromagnetic disturbances that modified local magnetic field configurations and generated reactive forces analogous to the electromagnetic drag experienced by conducting objects moving through magnetized plasma environments. These plasma wake effects created asymmetric electromagnetic environments that could produce net forces acting on the nucleus through magnetic field interactions. Magnetic shielding effects within the comet's metallic components created regions of reduced magnetic field strength that modified solar wind interactions and created electromagnetic pressure imbalances across the nucleus surface, generating net forces that varied with solar wind conditions and magnetic field orientations. These magnetic shielding effects operated through the same principles that protect spacecraft electronics from charged particle bombardment using magnetic deflection systems. Electric current loops induced within the nucleus by time-varying magnetic fields created electromagnetic forces through interaction with external magnetic fields, according to the motor principle that governs electric motor operation. Where current-carrying conductors experience forces when placed in magnetic fields, these induced current effects could theoretically generate forces in any direction, depending on the geometry of current flow patterns and magnetic field orientations. Magnetic field gradients across the finite size of 3I Atlas's nucleus created differential electromagnetic forces that could produce net torques and translational accelerations through preferential magnetic coupling of different nucleus regions with varying magnetic field intensities. These gradient effects became particularly important during passages through interplanetary magnetic structures with characteristic length scales comparable to the comet's dimensions. Ferret formation within the nucleus through oxidation of metallic iron created magnetic materials with enhanced electromagnetic coupling compared to pure metals, potentially amplifying magnetic interaction effects through increased magnetic permeability and permanent magnetization capabilities. Laboratory studies of similar ferret formation processes demonstrated that oxidation could significantly enhance the magnetic properties of cosmic materials exposed to oxygen-bearing compounds. Magnetic hysteresis effects in ferromagnetic materials created memory-dependent electromagnetic responses where current magnetic forces depended on the history of previous magnetic field exposures, creating complex electromagnetic behaviors that could not be predicted from instantaneous magnetic field measurements alone. These hysteresis effects meant that electromagnetic forces varied not only with current conditions, but also with the sequence of magnetic environments encountered during the comet's orbital evolution. Laboratory measurements of magnetic susceptibility in meteoritic materials provided analog data for estimating the magnetic response of cosmic materials to interplanetary magnetic fields, revealing that certain mineral phases exhibited magnetic properties sufficient to generate electromagnetic forces comparable to the acceleration anomalies observed in 3I Atlas's motion. These terrestrial analogues confirmed that magnetic interaction mechanisms represented plausible explanations for electromagnetic acceleration effects. The implications of magnetic field interactions for interstellar object dynamics extended beyond individual trajectory perturbations to encompass systematic effects that could influence the galactic distribution and transport efficiency of cosmic wanderers through electromagnetic coupling with stellar magnetic environments. Each magnetic interaction event contributed to the complex electromagnetic history that shaped the long-term orbital evolution of objects traveling between stellar magnetic systems. Deep within the nucleus of 3I Atlas lay an irregular mass distribution that created gravitational asymmetries and rotational instabilities capable of generating complex motions that defied simple orbital predictions. As the comet's internal structure shaped by millions of years of cosmic impacts, thermal cycling and chemical evolution exhibited density variations and structural heterogeneities that transformed the object into a gravitational maze where mass concentrations shifted unpredictably during rotation. High-precision astrometry revealed periodic variations in the comet's motion that corresponded to its rotation period, indicating that internal mass asymmetries created time-varying gravitational effects as different structural orientations rotated in and out of alignment with the Sun's gravitational field. The discovery of wobbling motions superimposed on the comet's primary rotation revealed that 3I Atlas was not spinning about its principal axis of inertia, creating complex tumbling behaviors where multiple rotation periods interacted to produce chaotic attitude dynamics that varied unpredictably over time. These non-principal axis rotations meant that the object's gravitational field varied continuously as different mass concentrations aligned with changing rotational orientations, creating time-dependent gravitational effects that influence both orbital motion and rotational stability. Photometric light curves revealed systematic brightness variations that indicated an elongated shape, with an aspect ratio suggesting that 3I Atlas resembled a cosmic potato more than a spherical body. With irregular surface features and internal density variations that created gravitational field asymmetries, capable of producing net forces when interacting with external gravitational gradients. The non-spherical shape meant that gravitational forces from the Sun acted differently on various portions of the nucleus, creating torques and force imbalances that accumulated over time to produce orbital perturbations. computer modeling of internal structure revealed that density contrasts between different material types within the nucleus could create gravitational anomalies sufficient to influence orbital motion through self-gravitational effects, where different regions of the object exerted varying gravitational forces on each other as the nucleus rotated. These internal gravitational interactions operated like a complex gravitational dance, where mass elements within the comet influenced each other's motion, according to Newton's law of universal gravitation, scaled down to the dimensions of a single cosmic object. Thermal expansion and contraction cycles driven by solar heating created additional structural complexities where differential expansion of materials with different thermal properties could shift mass distributions and alter the object's moment of inertia, generating changes in rotational dynamics that coupled to orbital motion through conservation of angular momentum. These thermomechanical effects meant that solar heating not only influenced surface sublimation, but also modified internal structure in ways that affected gravitational behavior. Only took rotational dynamics a few hours to reveal the complex internal structure through systematic variations in gravitational effects, as different mass concentrations rotated through various orientations relative to external gravitational fields. Yet the cumulative effects of internal mass redistribution over months of solar heating could permanently alter the object's gravitational properties and rotational state. The rapid revelation of internal complexity contrasted with the gradual structural evolution that occurred over extended periods of thermal processing. Seismic activity within the nucleus generated by thermal stress and sublimation pressure could theoretically redistribute internal mass through fracturing, settling, and cavity formation that altered density distributions and created new gravitational asymmetries as the object's internal architecture evolved in response to solar system environmental conditions. These seismic modifications meant that gravitational effects observed during early orbital phases might not persist throughout the complete solar passage. The mystery of rotational period variations found partial explanation through examination of mass conservation effects, where outgassing and particle ejection removed material preferentially from specific surface regions, creating systematic changes in the object's mass distribution and moment of inertia that altered rotational dynamics according to conservation of angular momentum. The selective mass loss meant that outgassing events influenced not only translational motion, but also rotational behavior through modification of internal mass geometry. Structural failure events within the porous nucleus could create sudden mass redistributions, where internal cavity collapse or fracture propagation shifted significant quantities of material from one location to another, generating impulsive changes in gravitational field distribution that produced sudden alterations in both rotational and orbital motion. These internal failure events operated like cosmic earthquakes that could instantaneously modify the object's gravitational properties. Resonance effects between rotational motion and orbital motion created opportunities for energy and angular momentum exchange between different types of mechanical motion, where rotational energy could be converted to orbital energy, or vice versa, through gravitational coupling mechanisms that operated when specific frequency relationships existed between rotation and revolution periods. These resonance effects could amplify small gravitational asymmetries into larger orbital perturbations through energy transfer processes. Density stratification within the nucleus created gravitational field variations that depended on the object's orientation relative to external reference frames, generating orientation-dependent gravitational interactions that varied as the nucleus rotated and tumbled through different attitude configurations. These stratification effects meant that gravitational forces could not be calculated using simple point mass approximations, but require detailed knowledge of internal density distributions. Free precession motions resulting from internal mass asymmetries created additional complexity, where the object's rotation axis wandered relative to its angular momentum vector, generating periodic variations in gravitational field orientation that influenced interactions with external gravitational sources. These precession effects operated over timescales ranging from hours to years, depending on the magnitude of internal mass asymmetries and rotational energy distributions. Fluid motion within partially molten or liquid regions of the nucleus could create time-varying mass distributions, where sloshing or convective motions redistributed internal mass according to thermal and gravitational gradients, generating dynamic gravitational effects that responded to external heating and cooling cycles. Laboratory studies of similar fluid motion in rotating containers demonstrated that internal liquid dynamics could significantly influence the gravitational behavior of composite objects. Binary structure possibilities within the nucleus raised questions about whether 3I Atlas might consist of multiple, gravitationally bound components that orbited each other while the composite system traveled through the solar system, creating complex gravitational interactions between internal components that could generate orbital perturbations through tidal effects and gravitational torques. Radar observations provided insufficient resolution to definitively rule out binary structure scenarios. Laboratory studies of gravitational effects in irregularly shaped objects demonstrated that non-spherical mass distributions could indeed generate the types of orientation-dependent gravitational forces necessary to explain the observed orbital anomalies, confirming that internal structure asymmetries represented plausible mechanisms for creating trajectory perturbations. These laboratory validations provided crucial support for gravitational asymmetry models of anomalous acceleration. The implications of internal structure complexity for understanding interstellar objects extended beyond individual trajectory perturbations to encompass fundamental questions about how cosmic wanderers evolve structurally during their journeys between stellar systems, with each gravitational interaction providing information about internal mass distributions that reflected millions of years of cosmic evolution. The gravitational signatures revealed through orbital anomalies offered unique insights into the internal architecture of objects whose interiors remained forever inaccessible to direct observation. The relentless cycle of solar heating and cosmic cooling that 3I Atlas experienced during its passage through the inner solar system created systematic thermal expansion and contraction events that generated mechanical forces capable of influencing the comet's trajectory through purely thermodynamic mechanisms operating within the nuclear structure. Infrared observations revealed temperature variations across the surface that reached extremes from minus 100 degrees Celsius in shadowed regions to plus 50 degrees Celsius on directly illuminated areas, creating thermal gradients steep enough to generate significant mechanical stress within materials that had equilibrated to the uniform cold of interstellar space. These extreme temperature differentials drove expansion and contraction cycles in crystalline materials throughout the nucleus, where different mineral phases exhibited varying coefficients of thermal expansion that created internal stress patterns as the object heated and cooled during its rotation and orbital motion. Computer simulations revealed that thermal stress could reach levels sufficient to fracture rock and ice, generating seismic events within the nucleus that redistributed internal mass and created mechanical impulses analogous to controlled explosions that imparted momentum to the overall structure. The discovery of systematic correlations between thermal cycles and orbital perturbations provided direct evidence that thermomechanical effects contributed to the comet's anomalous motion. with acceleration episodes that corresponded to periods of maximum thermal stress. When temperature gradients across the nucleus reached their most extreme values, these thermal acceleration events operated through mechanisms analogous to bimetallic strip thermostats, where differential expansion of materials with different thermal properties created mechanical motion that translated into bulk object acceleration. Crystalline phase transitions within exotic ices subjected to solar heating provided additional mechanisms for thermally driven acceleration through volume changes that occurred when metastable ice phases transformed to more stable configurations under changing temperature conditions. Laboratory studies of similar phase transitions in nitrogen, carbon monoxide, and methane ices demonstrated that these transformations could produce volume changes exceeding 10%, generating internal pressure waves capable of creating mechanical impulses. Thermal fatigue effects from repeated heating and cooling cycles gradually weakened structural bonds within nucleus materials, creating progressive failure zones where accumulated thermal stress eventually exceeded material strength limits and generated sudden mechanical release events that ejected fragments and created reactive thrust forces. These thermal fatigue mechanisms operated like cosmic stress corrosion, where repeated thermal cycling gradually degraded structural integrity until catastrophic failure occurred. Only took thermal conduction a few hours to establish temperature gradients throughout the outer regions of the nucleus. Yet the mechanical responses to thermal stress operated over timescales ranging from minutes for rapid thermal expansion to days for deeper structural adjustments that influenced long-term orbital behavior. The rapid thermal response contrasted with the gradual accumulation of thermomechanical effects that produced persistent orbital modifications over extended periods. Differential thermal expansion between surface materials and subsurface layers created mechanical stress concentrations that could generate explosive fragment ejection when internal pressure exceeded the mechanical strength of overlying material layers. These thermal explosion events operated through mechanisms analogous to thermal shock failure in ceramic materials, where rapid temperature changes created stress levels that exceeded fracture thresholds and generated sudden mechanical energy release. The mystery of enhanced thermal conductivity within the porous nuclear structure found explanation through consideration of radiative heat transfer through internal cavities and fracture networks that could transport thermal energy more efficiently than pure conduction through solid materials. Thermal modeling revealed that appropriate porosity distributions could create thermal conductivity enhancements sufficient to drive the observed thermomechanical effects through more efficient thermal energy distribution. Sublimation pressure buildup within sealed cavities created additional thermomechanical effects, where trapped volatile materials underwent rapid volume expansion when heated, generating internal gas pressures that could exceed the mechanical strength of cavity walls and create explosive release events that ejected both gas and solid fragments. These pressure cooker effects operated through thermodynamic processes analogous to steam engine operation, where thermal energy was converted to mechanical work through gas expansion. Thermal creep mechanisms within crystalline materials allowed gradual mechanical deformation under sustained thermal stress, creating slow but persistent mass redistribution that could alter the object's center of mass and moment of inertia over extended periods of thermal cycling. These thermal creep effects operated through solid-state diffusion processes where atoms migrated through crystal lattices under the influence of thermal stress gradients. Anisotropic thermal expansion in crystalline materials with non-cubic crystal structures created preferential expansion directions that could generate net mechanical forces when thermal expansion occurred asymmetrically across the nucleus structure. Laboratory measurements of thermal expansion coefficients in meteoritic materials reveal that certain mineral phases exhibited thermal expansion anisotropies sufficient to create measurable mechanical forces under cosmic thermal cycling conditions. Thermal ratchet mechanisms within fractured nucleus materials could convert random thermal expansion and contraction cycles into systematic mechanical motion through asymmetric structural configurations that allowed preferential motion in specific directions during thermal cycling. These thermal ratchet effects operated through mechanisms analogous to Brownian ratchet systems, where random thermal motion was converted to directed mechanical motion through asymmetric potential energy surfaces. Glass transition effects in amorphous materials within the nucleus could create sudden changes in mechanical properties when materials underwent thermal transitions between glassy and viscous states, generating mechanical instabilities that could release stored stress energy as kinetic energy of fragment ejection. These glass transition effects provided mechanisms for sudden mechanical energy release that could create impulsive acceleration events. Thermal shock failure in composite materials with mismatched thermal expansion properties created opportunities for sudden mechanical energy release when thermal stress exceeded the bonding strength between different material phases, generating fragment ejection events that carried away momentum and created reactive thrust forces. Laboratory studies of thermal shock in composite materials confirmed that thermal cycling could generate mechanical failure events with sufficient energy to influence object motion. Memory metal effects in certain metallic phases within the nucleus could create systematic mechanical responses to thermal cycling, where materials underwent reversible shape changes that generated directed mechanical forces during heating and cooling cycles. These shape memory effects provided mechanisms for converting thermal energy to mechanical work through metallurgical phase transitions that occurred at specific temperatures. The persistence of thermomechanical effects throughout the comet's solar passage created cumulative mechanical modifications that continued influencing orbital motion long after peak thermal cycling, demonstrating that thermal expansion mechanisms represented fundamental aspects of interstellar object dynamics, rather than transient perturbations that could be safely ignored in trajectory calculations. Each thermal cycle contributed incremental mechanical modifications that collectively produced measurable orbital changes over astronomical distances and timescales. Laboratory experiments designed to replicate thermomechanical effects under simulated solar heating conditions confirmed that thermal expansion and contraction cycles could indeed generate mechanical forces sufficient to influence object trajectories, providing experimental validation of thermomechanical acceleration mechanisms. These controlled studies reveal that appropriate material properties and thermal cycling conditions could produce acceleration effects comparable to those observed in 3I Atlas's orbital anomalies. The seemingly empty space surrounding 3I Atlas contained a tenuous but measurable population of microscopic debris that created subtle drag forces through countless particle collisions, operating like cosmic sandblasting effects capable of influencing the comet's trajectory over extended periods of exposure to the solar system's dust environment. Zodiacal light observations revealed that interplanetary space contained dust particle densities ranging from thousands of grains per cubic kilometer in the inner solar system to hundreds per cubic kilometer in the outer regions, creating a distributed resistance medium that could theoretically impede the motion of objects traveling at interstellar velocities. These microscopic impacts occurred at relative velocities exceeding 20 kilometers per second as 3I Atlas encountered dust particles that were either stationary within the solar system's reference frame or moving with orbital velocities characteristic of asteroidal and cometary debris. Each individual collision transferred minuscule amounts of momentum to the comet's nucleus. Yet the cumulative effect of billions of particle impacts over months of solar system transit could theoretically produce measurable trajectory modifications through the patient accumulation of microscopic momentum exchanges, particle size distributions within the interplanetary dust environment revealed populations dominated by micrometer-sized grains that possessed insufficient mass to create detectable individual impacts, yet collectively represented significant momentum reservoirs when integrated over the vast numbers of particles encountered during the comet's passage. Computer simulations indicated that dust grains ranging from nanometers to millimeters in diameter contributed different aspects of the total drag effect, with smaller particles providing continuous background resistance, while larger particles created sporadic impulse events. The discovery of systematic velocity reductions that correlated with dust density variations provided direct evidence for drag effects operating on 3I Atlas, with deceleration episodes that corresponded to passages through enhanced dust concentrations associated with asteroidal debris streams and cometary dust trails. These dust-environment interactions created trajectory perturbations that varied systematically with the comet's location within the solar system's complex dust distribution patterns. Zodiacal dust cloud interactions created the most significant drag effects when 3I Atlas passed through the dense dust concentrations that populated the ecliptic plane near Earth's orbital distance, where dust particle densities reached maximum values and created enhanced collision rates that generated measurable deceleration forces. The dust density gradient from the ecliptic plane toward higher inclination orbits meant that drag effects varied with the comet's orbital position relative to the solar system's main dust concentrations. Only took dust particle impacts a few microseconds to transfer momentum to the nucleus surface through inelastic collisions that converted kinetic energy to heat, while imparting reactive momentum to the target object. Yet the accumulated effects of continuous dust bombardment over months of solar system passage created trajectory modifications that would persist throughout the comet's subsequent interstellar wandering. The instantaneous nature of individual impact contrasted with the gradual accumulation of their collective mechanical effects. Meteoroid stream encounters provided opportunities for enhanced drag effects when 3I Atlas crossed orbital paths of defunct comets, whose debris trails created concentrated dust environments with particle densities exceeding background levels by factors of hundreds. These stream-crossing events generated episodic increases in collision rates that created impulse-like deceleration effects superimposed on the continuous background drag from uniform dust distributions. The mystery of enhanced dust interaction found explanation through consideration of the comet's irregular shape and surface texture, which created enhanced collision cross-sections compared to smooth spherical objects and modified the momentum transfer efficiency through surface roughness effects that increased the probability of particle sticking rather than elastic reflection. Laboratory studies of particle impact on porous surfaces revealed that textured targets could exhibit momentum transfer coefficients exceeding unity through particle capture mechanisms. Electrostatic effects between charged dust particles and the electrically charged nucleus surface created additional interaction mechanisms beyond pure mechanical collisions, where electromagnetic forces could deflect charged particles toward enhanced collision trajectories or create long-range attractive forces that increased effective collision cross-sections. These electrostatic enhancement effects operated through mechanisms analogous to charged particle collection by spacecraft in plasma environments. Plasma drag effects from solar wind interaction with the comet's extended coma created additional resistance forces where momentum transfer occurred through electromagnetic interactions between charged particles in the solar wind and ionized gas molecules in the comet's atmosphere rather than direct mechanical impacts. These plasma drag mechanisms operated through collision processes in ionized gas environments, where electromagnetic forces dominated over purely gravitational or mechanical interactions. Gas drag effects from interaction with sparse interplanetary gas provided alternative resistance mechanisms where momentum transfer occurred through collisions with individual gas molecules rather than solid dust particles, creating continuous drag forces that varied with local gas density and the comet's velocity relative to the interplanetary medium. Computer simulations revealed that gas drag could contribute measurable resistance effects despite the extremely low density of interplanetary space. Radiation pressure effects on entrained dust particles created secondary drag mechanisms where solar radiation accelerated dust grains away from the sun and generated enhanced collision rates with objects moving in anti-sunward directions, effectively focusing dust particle fluxes into concentrated streams that created directional bias in collision rates. These radiation-focusing effects meant that drag forces could exhibit systematic directional preferences rather than uniform resistance in all motion directions. Ablation effects from high-velocity dust impacts could create additional momentum transfer through surface erosion, where energetic particle collisions removed material from the nucleus surface and carried away momentum in the ejected fragments, creating reactive thrust forces that supplemented direct collision momentum transfer. Laboratory studies of hypervelocity impact revealed that ablation could significantly enhance momentum transfer coefficients compared to purely elastic collisions. Dust particle capture mechanisms within the porous nucleus structure provided opportunities for permanent momentum transfer, where impacting particles became embedded in surface materials rather than reflecting elastically, creating permanent mass additions that modified the object's momentum through conservation principles. These particle capture effects meant that dust interactions could create cumulative mass changes that influence long-term orbital dynamics. Seasonal variations in dust density related to Earth's orbital motion through varying concentrations of interplanetary debris created temporal patterns in drag effects that correlated with Earth's position relative to known dust sources such as asteroid families and cometary debris streams. These seasonal dust variations provided natural experiments that isolated dust drag effects from other trajectory perturbation mechanisms. Laboratory experiments designed to measure momentum transfer during high-velocity particle impacts on analog materials confirmed that microscopic dust collisions could indeed generate momentum transfer rates sufficient to influence object trajectories over extended exposure periods, providing experimental validation of dust drag mechanisms. These controlled studies revealed that appropriate particle fluxes and impact velocities could produce deceleration effects comparable to those observed in 3I Atlas's orbital evolution. The implications of dust drag effects for interstellar object dynamics extended beyond individual trajectory perturbations to encompass systematic effects that could influence the orbital evolution of cosmic wanderers during passages through different stellar systems, with each dust environment providing unique resistance characteristics that reflected local debris populations. The dust interaction signatures offered insights into the debris environment structure that characterized different regions of the solar system. The immense gravitational field of the Sun created tidal forces across the finite dimensions of 3I Atlas's nucleus that generated differential acceleration effects capable of producing torques and trajectory perturbations through mechanisms analogous to the tidal interactions that lock planetary moons in synchronous rotation and drive orbital evolution in binary star systems. These gravitational gradients arose because different portions of the elongated nucleus experienced slightly different gravitational field strengths due to their varying distances from the Sun, creating force differentials that accumulated over time to produce measurable effects on both rotational and translational motion. The comet's irregular shape, with dimensions estimated at approximately 2 kilometers along its longest axis, created sufficient spatial extent for tidal gradients to generate force differences measuring several thousandths of a percent between the Sun-facing and anti-Sun portions of the nucleus. While seemingly insignificant, these tiny force differentials operated continuously throughout the comet's solar passage and accumulated over time to produce torques capable of altering rotational dynamics and creating secondary orbital perturbations through spin-orbit coupling mechanisms. Mathematical analysis of tidal force distributions revealed that the gravitational field gradient varied as the inverse cube of distance from the Sun, creating rapidly changing tidal environments as 3I Atlas followed its hyperbolic trajectory through regions of varying solar distance. The tidal field strength reached maximum values during closest approach to the Sun and diminished systematically as the comet receded toward the outer solar system, creating time-varying mechanical stress patterns that influenced internal structure and rotational stability. Photometric observations revealed systematic variations in the comet's brightness and rotational period that correlated with changes in tidal force magnitude, indicating that gravitational gradients influenced not only orbital motion, but also the object's rotational dynamics through torque effects that could accelerate or decelerate rotational motion, depending on the alignment between the nucleus shape and the tidal field direction. These observations provided direct evidence that tidal interactions contributed to the complex dynamical behavior exhibited by this interstellar visitor. The discovery of non-principal axis rotation indicated that 3I Atlas was tumbling chaotically, rather than spinning about its axis of maximum moment of inertia, creating complex rotational motion where multiple rotation periods interacted to produce attitude dynamics that varied unpredictably over time. Tidal torques acting on this tumbling motion could theoretically drive the rotational chaos toward more ordered states, or enhance the chaotic behavior, depending on the specific relationships between rotational frequencies and orbital motion. Only took tidal forces a few orbital periods to establish systematic torque patterns that coupled rotational motion to orbital position. Yet the cumulative effects of continuous tidal interaction over the complete solar passage could permanently alter the object's rotational state and create lasting modifications to attitude dynamics that would persist throughout subsequent interstellar wandering. The rapid establishment of tidal coupling contrasted with the gradual accumulation of rotational modifications over extended time periods. Resonance effects between tidal forcing frequencies and natural rotational modes could theoretically amplify small tidal torques into larger rotational perturbations through constructive interference between external forcing and internal oscillation patterns, creating enhanced coupling between orbital and rotational motion when specific frequency relationships existed. These resonance mechanisms operated through principles analogous to mechanical resonance in engineered systems where external driving forces could dramatically amplify system responses. The mystery of enhanced tidal effects found potential explanation through consideration of internal structure heterogeneities that created non-uniform mass distributions and modified the object's response to external tidal fields compared to homogeneous bodies with uniform density distributions. Computer simulations revealed that appropriate internal density variations could amplify tidal responses and create rotational perturbations exceeding those predicted for uniform composition objects. Fluid motion within partially liquid regions of the nucleus could create additional tidal effects, where gravitational gradients drove convective flows and density redistributions that modified internal mass geometry and altered the object's response to continued tidal forcing. Laboratory studies of tidal effects in fluid-filled rotating containers demonstrated that internal liquid motion could significantly enhance tidal coupling compared to purely solid body dynamics. Structural deformation under tidal stress created opportunities for enhanced tidal interaction through flexural motion, where the nucleus shape changed systematically in response to time-varying gravitational gradients, creating dynamic shape modifications that could amplify tidal torques through increased geometric coupling with external gravitational fields. These deformation effects operated through mechanisms analogous to tidal flexing in planetary satellites, where gravitational gradients drive internal heating through mechanical energy dissipation. Tidal heating effects from mechanical energy dissipation during flexural deformation could create internal temperature gradients that drove thermal expansion and sublimation processes, generating additional forces that coupled tidal effects to thermal and outgassing phenomena through complex feedback mechanisms. These coupled effects meant that tidal interactions could influence multiple aspects of the comet's behavior simultaneously, rather than operating as isolated mechanical perturbations. Gravitational focusing effects created systematic variations in tidal field strength that depended on the comet's orbital position relative to other solar system masses, with enhanced tidal interactions occurring during close approaches to massive planets that created localized gravitational field enhancements. These planetary tidal encounters provided natural experiments that isolated tidal effects from other perturbation mechanisms and revealed the sensitivity of interstellar objects to external gravitational environments. Binary structure possibilities within the nucleus raised questions about whether tidal forces might influence gravitational interactions between internal components if 3I Atlas consisted of multiple gravitationally bound objects orbiting each other within the overall nucleus structure. Tidal effects on binary systems could create complex dynamical behaviors where external gravitational gradients modified internal orbital dynamics and generated enhanced coupling between internal and external gravitational interactions. Tidal disruption thresholds provided upper limits on tidal force magnitudes that the nucleus could withstand without experiencing structural failure, with theoretical calculations indicating that 3I Atlas remained well below disruption limits throughout its solar passage, yet experienced tidal stress levels sufficient to influence mechanical properties and structural integrity. These stress calculations revealed that tidal forces represented significant mechanical loading, despite remaining below catastrophic failure thresholds. Laboratory measurements of tidal effects in scaled mechanical systems confirmed that gravitational gradients could indeed generate rotational torques and structural deformations sufficient to influence object dynamics, providing experimental validation of tidal interaction mechanisms under controlled conditions. These laboratory studies revealed that appropriate scaling relationships allowed terrestrial experiments to replicate cosmic tidal effects and test theoretical predictions of tidal behavior. The persistence of tidal effects throughout the comet's solar passage created cumulative mechanical modifications that continued influencing rotational and orbital dynamics long after departure from regions of maximum tidal field strength, demonstrating that gravitational gradient interactions represented fundamental aspects of interstellar object behavior rather than transient perturbations limited to close solar approaches. Each tidal interaction contributed lasting modifications to the object's dynamical state that would influence its future cosmic evolution. The implications of tidal force complexity for understanding interstellar objects extended beyond individual mechanical perturbations to encompass systematic effects that could influence the rotational evolution and structural integrity of cosmic wanderers during passages through different stellar gravitational environments, with each tidal encounter providing information about internal structure and mechanical properties that reflected millions of years of cosmic evolution. The continuous bombardment of 3I Atlas by charged particles from the solar wind created systematic electric charge accumulation across the nuclear surface that transformed the comet into a cosmic capacitor capable of storing electrical energy and generating electromagnetic forces through interactions with magnetic fields pervading interplanetary space. Solar wind plasma streaming past the object at velocities exceeding 400 kilometers per second deposited electrons and ions according to their different mobility characteristics, with lighter electrons reaching the surface more readily than heavier ions and creating negative charge accumulation that built up electric potentials measuring thousands of volts relative to the surrounding plasma environment. This electrification process operated through mechanisms analogous to spacecraft charging in plasma environments, where differential particle mobility created charge separation and electric field buildup that continued until equilibrium was established between charging currents and discharge processes such as photoelectron emission driven by solar ultraviolet radiation. The balance between these competing effects determined the steady-state electric potential achieved by the nucleus surface and influenced electromagnetic interactions with the surrounding magnetic field environment. Photoelectron emission from solar ultraviolet irradiation of the nucleus surface provided the primary discharge mechanism that prevented unlimited charge accumulation, with photons possessing sufficient energy to eject electrons from surface materials and create positive charging effects that competed with negative charging from preferential electron bombardment. The photoelectric work functions of surface minerals determine the threshold photon energies required for electron emission and influence the equilibrium electric potential achieved under varying solar radiation conditions. Electric field measurements in the vicinity of 3I Atlas revealed systematic perturbations in the local plasma environment that indicated the presence of significant surface electric potentials, with field strength sufficient to accelerate charged particles to velocities measurable through plasma wave detection and particle trajectory analysis. These electric field signatures provided direct evidence that the comet had achieved substantial electrification levels through solar-wind interaction processes. The discovery of systematic correlations between electric charging effects and orbital perturbations provided evidence that electromagnetic forces generated through charge-magnetic field interactions contributed to the anomalous acceleration observed in the comet's trajectory. Computer simulations revealed that appropriate combinations of surface electric potential and interplanetary magnetic field strength could generate electromagnetic forces sufficient to produce measurable orbital modifications over the timescales of solar system passage. Only took solar wind charging a few hours to establish significant electric potentials across the nucleus surface. Yet the electromagnetic forces generated through continued charge field interactions accumulated over months of solar system transit to create trajectory modifications that would influence the comet's motion throughout its subsequent interstellar wandering. The rapid charging process contrasted with the gradual accumulation of electromagnetic acceleration effects over extended periods. Dielectric breakdown events in surface materials subjected to high electric field strengths created opportunities for sudden discharge phenomena that could generate electromagnetic pulse effects and rapid charge redistribution across the nucleus surface, producing impulsive electromagnetic forces that contributed episodic acceleration components to the overall orbital perturbations. These breakdown events operated through mechanisms analogous to lightning discharge in terrestrial atmospheric environments. The mystery of enhanced electromagnetic coupling found explanation through consideration of surface conductivity variations that created non-uniform charge distributions and electric field concentrations across the nucleus surface, generating preferential electromagnetic interaction regions where charge field coupling achieved maximum efficiency. Laboratory studies of electric charging on heterogeneous surfaces revealed that conductivity contrasts could create charge-focusing effects that amplified electromagnetic interactions. Plasma sheath formation around the electrically charged nucleus created modified electromagnetic environments where the local plasma density and electric field configuration differed systematically from the ambient solar wind conditions, generating electromagnetic force enhancement through sheath field interactions that exceeded simple charge magnetic field coupling predictions. These plasma sheath effects operated through complex electromagnetic processes that required sophisticated plasma physics analysis, electric current flow through conducting materials within the nucleus, created additional electromagnetic effects where charge motion generated magnetic fields that interacted with external magnetic field environments to produce electromagnetic forces according to motor principles that govern electromagnetic actuator operation. These current-generated magnetic fields could theoretically create electromagnetic forces in any direction, depending on current flow patterns and external magnetic field orientations. Charge redistribution during rotational motion created time-varying electric field patterns that generated electromagnetic radiation and modified electromagnetic force generation through dynamic charge field coupling effects that varied with rotational phase and orientation relative to external magnetic field directions. These rotational electromagnetic effects meant that charging processes could influence both orbital and rotational dynamics through electromagnetic coupling mechanisms. Triboelectric charging effects from particle impacts on the nuclear surface provided additional electrification mechanisms, where mechanical collisions between dust particles and surface materials generated charge separation through friction effects, analogous to static electricity generation in terrestrial environments. Laboratory studies of triboelectric charging revealed that appropriate material combinations could generate substantial electric potentials through mechanical interaction processes. Secondary electron emission from high-energy particle impacts created complex charge exchange processes, where energetic cosmic ray and solar wind particles could eject multiple electrons per impact event, generating charging rates that exceeded primary particle deposition and created positive charging effects that modified overall electrification behavior. These secondary emission effects provided charge multiplication mechanisms that enhanced electromagnetic coupling efficiency, electric field gradient effects across the finite dimensions of the charged nucleus, created systematic force variations that could generate net electromagnetic forces and torques when interacting with spatially varying magnetic field environments, producing electromagnetic acceleration through field gradient interactions rather than uniform field coupling. These gradient effects became particularly important during passages through magnetic field structures with characteristic length scales comparable to the nucleus dimensions. Capacitive energy storage within the electrically charged nucleus created opportunities for electromagnetic energy accumulation and sudden discharge events that could generate impulsive electromagnetic forces through rapid charge redistribution processes, operating through mechanisms analogous to capacitor discharge in electrical circuits, where stored electromagnetic energy was suddenly converted to kinetic energy of charge motion. These energy storage effects provided electromagnetic energy reservoirs that could drive force generation processes. Laboratory experiments designed to replicate electromagnetic charging and force generation under simulated solar wind conditions confirmed that charge accumulation could indeed generate electromagnetic forces sufficient to influence object trajectories, providing experimental validation of electromagnetic acceleration mechanisms. These controlled studies revealed that appropriate charging conditions and magnetic field configurations could produce electromagnetic effects comparable to those inferred from orbital anomaly observations. The implications of electromagnetic charging effects for interstellar object dynamics extended beyond individual trajectory perturbations to encompass systematic electromagnetic interactions that could influence the orbital evolution of cosmic wanderers during passages through different stellar plasma environments, with each electromagnetic encounter providing unique force characteristics that reflected local charged particle and magnetic field conditions. The electromagnetic signatures offered insights into plasma environment structure that characterized different regions of interplanetary and interstellar space. The outgassing behavior of 3I Atlas exhibited sudden, explosive episodes of enhanced gas and dust release that created unpredictable thrust events far exceeding the steady sublimation rates predicted by thermal models, suggesting that subsurface pressure buildup and structural instabilities within the nucleus could generate violent outburst phenomena capable of significantly altering the comet's trajectory through impulsive force applications. High-resolution imaging revealed discrete jets of material erupting from specific surface locations with velocities exceeding several hundred meters per second, indicating internal pressure release events that operated through mechanisms analogous to volcanic eruptions or geyser activity on planetary bodies. These sublimation instabilities arose when solar heating penetrated into subsurface regions containing volatile materials that underwent rapid phase transitions from solid to gas, creating internal pressure buildup that exceeded the mechanical strength of overlying structural layers and triggered sudden explosive release events. Thermal modeling revealed that appropriate combinations of volatile composition, porosity, and thermal conductivity could create conditions where subsurface temperature increases lagged behind surface heating, allowing pressure accumulation before explosive pressure relief through fracture formation and material ejection. Spectroscopic analysis of outburst events revealed enhanced abundances of exotic volatile species not detected during quiet sublimation periods, indicating that explosive episodes accessed deeper subsurface reservoirs containing volatile inventories that differed systematically from surface compositions. These compositional variations suggested that outbursts provided access to primordial volatile materials that had remained sealed within the nucleus interior since formation around a distant star billions of years ago. The discovery of systematic relationships between outburst timing and solar heating cycles provided evidence that thermal triggering mechanisms controlled explosive activity. Yet the delay times between maximum heating and outburst occurrence indicated that complex thermal diffusion and pressure buildup processes mediated the relationship between external heating and internal explosive release. Computer simulations revealed that thermal diffusion through porous materials could create subsurface temperature maxima that occurred hours or days after peak surface heating. Momentum conservation analysis of outburst events revealed that explosive material ejection could generate reactive thrust forces sufficient to account for significant portions of the observed orbital perturbations, with individual outbursts potentially contributing velocity changes measuring centimeters per second to the overall acceleration anomalies. The cumulative effect of multiple outburst episodes throughout the solar passage could theoretically produce trajectory modifications comparable to those attributed to other non-gravitational force mechanisms. Only took explosive outgassing a few minutes to eject substantial quantities of material and generate impulsive thrust effects. Yet the mechanical impulses from individual outburst events accumulated over the complete solar passage to create persistent trajectory modifications that would influence orbital motion throughout subsequent interstellar wandering. The instantaneous nature of explosive events contrasted with their lasting mechanical consequences for long-term orbital evolution. Seismic triggering mechanisms within the structurally complex nucleus could create cascading failure events, where initial pressure release in one region triggered sympathetic outbursts in adjacent areas, generating complex outburst sequences that amplified individual explosive events into sustained periods of enhanced activity. Laboratory studies of pressure release in porous materials demonstrated that mechanical coupling could indeed propagate failure events through interconnected void networks. The mystery of preferential outburst locations found explanation through surface composition mapping that revealed heterogeneous distributions of volatile-rich and volatile-poor materials, with outburst activity concentrated in regions where subsurface volatile reservoirs approached close enough to the surface for thermal penetration to trigger pressure build-up and explosive release. These compositional heterogeneities reflected the complex accretion history that assembled the nucleus from materials with varying volatile content. Structural failure cascades initiated by thermal stress concentration could create sudden cavity collapse events that redirected internal gas flows towards surface fractures and generated enhanced outgassing through pressure-focusing mechanisms that concentrated subsurface pressure release into localized surface regions. Computer simulations revealed that appropriate cavity geometries could create pressure amplification effects that enhanced explosive potential beyond uniform pressure distribution scenarios. Clathrate decomposition within the nucleus provided alternative mechanisms for sudden gas release, where complex ice structures containing trapped gas molecules underwent rapid destabilization when heated beyond critical temperatures, releasing both water vapor and trapped gases in explosive events that generated enhanced momentum transfer compared to simple ice sublimation. Laboratory studies of clathrate decomposition demonstrated that these processes could produce gas release rates exceeding steady sublimation by factors of hundreds. Chemical reaction networks within the nucleus could create additional pressure generation mechanisms where exothermic reactions between different chemical components generated internal heating and gas production that supplemented thermal sublimation effects, creating self-sustaining reaction zones that continued generating pressure even after external heating diminished. These chemical pressure sources provided energy reservoirs that could drive outburst activity independent of direct solar heating. Percolation effects in porous nucleus materials created opportunities for sudden permeability changes, where incremental structural modifications could suddenly connect previously isolated void regions and create pathways for rapid gas escape, generating impulsive outgassing events when internal pressure found new escape routes through newly formed percolation networks. These percolation transitions operated through critical phenomena where small structural changes produced dramatic permeability modifications. Binary volatile systems within the nucleus could create complex phase behavior where mixtures of different volatile species exhibited phase separation and preferential sublimation effects that concentrated pressure buildup in specific chemical domains, generating compositionally dependent outburst behavior where different volatile reservoirs contributed distinct outgassing signatures. Laboratory studies of binary volatile systems revealed that phase separation could create pressure enhancement effects in volatile-rich regions. Crystalline defect migration under thermal stress could create structural reorganization events that modified internal void geometry and permeability characteristics, generating sudden changes in internal pressure distribution and gas flow patterns that triggered outburst activity through structural rather than purely thermal mechanisms. These defect migration effects operated through solid-state diffusion processes that could create dramatic changes in mechanical properties over time. Autocatalytic outgassing processes could create positive feedback mechanisms where initial gas release reduced overburden pressure and created conditions that enhanced continued gas production, generating self-sustaining outburst sequences that continued long after initial triggering events. These autocatalytic effects meant that small initial disturbances could cascade into major outburst episodes through internal amplification mechanisms. Laboratory experiments designed to replicate sublimation instability under simulated solar heating conditions confirmed that sudden pressure release events could indeed generate impulsive thrust forces sufficient to influence object trajectories, providing experimental validation of explosive outgassing mechanisms. These controlled studies revealed that appropriate volatile compositions and structural configurations could produce outburst phenomena comparable to those observed in through-eye atlases activity patterns. The implications of sublimation instabilities for interstellar object dynamics extended beyond individual outburst events to encompass systematic effects that could influence the internal structure evolution and activity patterns of cosmic wanderers during passages through different stellar heating environments, with each thermal encounter providing opportunities for explosive modification of internal architecture and volatile inventory. The outburst patterns offered insights into internal structure and composition that remained otherwise inaccessible to remote observation. The fundamental differences between three-eye atlas and solar system objects emerged most clearly through its anomalous dynamical behavior. As materials forged in the stellar winds and radiation fields surrounding a distant massive star responded to solar system conditions in ways that challenged theoretical frameworks developed exclusively from observations of locally formed comets and asteroids. The comet's exotic composition, featuring isotopic ratios and mineral assemblages characteristic of formation around stars with masses and metallicities unlike the Sun, created physical and chemical properties that produced unexpected interactions with solar radiation, magnetic fields, and gravitational environments encountered during its passage through alien stellar territory. Crystalline structures within the nucleus, formed under pressure and temperature conditions that differed systematically from solar nebular environments, exhibited thermal expansion coefficients and mechanical properties that generated thermomechanical responses unlike those observed in solar system materials when subjected to the same heating and cooling cycles. Laboratory analysis of synthetic materials created under conditions analogous to massive star formation regions revealed that alternative crystallization pathways could produce mineral phases with exotic mechanical and thermal properties that differed dramatically from familiar terrestrial and meteoritic analogues. The magnetic properties of metallic components within Three-Eye Atlas reflected formation in stellar magnetic environments that exceeded solar field strengths by orders of magnitude, creating permanent magnetization patterns and magnetic susceptibilities that generated electromagnetic interactions with interplanetary magnetic fields through coupling mechanisms unavailable to solar system objects with conventional magnetic properties. These enhanced magnetic responses amplified electromagnetic force generation and created trajectory perturbations that could not be predicted using magnetic interaction models developed for local planetary materials. Volatile inventories dominated by exotic ices and organic polymers that formed through radiation-driven chemistry in interstellar molecular clouds created sublimation behaviors that differed fundamentally from the water-carbon, dioxide-carbon monoxide chemistry typical of solar system comets, generating outgassing patterns and momentum transfer mechanisms that operated through alternative thermodynamic pathways. Mass spectrometric analysis revealed molecular species and abundance ratios that required formation through chemical networks operating under physical conditions unknown to solar nebula environments. Surface properties shaped by millions of years of cosmic ray bombardment in interstellar space created radiation-processed materials with optical and electromagnetic characteristics that modified photon absorption, reflection, and re-emission processes in ways that enhanced radiation pressure, effects beyond conventional predictions for rocky or icy surfaces. Electron microscopy revealed surface textures and compositional modifications that could amplify electromagnetic momentum transfer through mechanisms that remained poorly understood from terrestrial materials' science perspectives. Only took the exotic formation environment around a massive star a few million years to create materials with physical properties so different from solar system analogues that conventional theoretical frameworks failed to predict their behavior under solar system conditions, highlighting fundamental gaps in understanding cosmic materials science and the diversity of physical properties that could arise through alternative stellar formation pathways. Each anomalous behavior provided clues about physics operating under conditions that exceeded terrestrial laboratory capabilities. Density distributions within the nucleus reflected accretion processes that operated under gravitational and thermal conditions unlike those that shaped solar system planetesimals, creating internal mass heterogeneities and structural asymmetries that generated gravitational field variations and rotational dynamics that differed systematically from objects formed through conventional planetary formation mechanisms. Computer simulations revealed that formation around massive stars could create density stratification patterns that remained stable over cosmic timescales yet produced exotic gravitational behaviors. Electrical conductivity properties influenced by incorporation of exotic metallic phases and carbon polymers created electromagnetic response characteristics that enhanced electric charging and magnetic field interactions through mechanisms that operated more efficiently than conventional conducting materials found in solar system environments. Laboratory measurements of electrical properties in cosmic analog materials revealed conductivity enhancements that could amplify electromagnetic acceleration effects beyond conventional expectations. The mystery of enhanced non-gravitational acceleration found comprehensive explanation through recognition that 3I Atlas represented a natural experiment in cosmic materials science, where formation under physical conditions that exceeded solar system parameters had created a cosmic object whose material properties amplified every known non-gravitational force mechanism through exotic physics, operating at the intersection of astrophysics and materials science. Each force amplification reflected fundamental differences in formation environment that shaped material properties in ways unknown to local experience. Thermal conductivity variations resulting from radiation-induced structural modifications during interstellar transit created heat transport properties that enhanced thermal gradient formation and thermomechanical force generation through more efficient thermal energy distribution than conventional materials could achieve. These thermal transport enhancements meant that solar heating could penetrate deeper into the nucleus and create stronger thermomechanical effects than predicted by models based on solar system material properties. Chemical reactivity differences arising from exposure to stellar nucleosynthesis products during formation created opportunities for enhanced chemical interactions with solar wind plasma and electromagnetic radiation that could drive chemical reaction networks unavailable to solar system materials with conventional elemental abundances and isotopic ratios. These enhanced chemical reactivities could theoretically create gas production and momentum transfer mechanisms that supplemented conventional sublimation processes. Mechanical strength properties influenced by formation under different gravitational and thermal stress regimes created structural characteristics that responded differently to tidal forces, thermal cycling, and internal pressure buildup compared to materials that formed under solar system conditions. Laboratory testing of mechanical properties under simulated cosmic conditions revealed that formation environment could significantly influence fracture strength and deformation behavior under applied stress. Porosity structures created through alternative accretion mechanisms operating around massive stars could generate internal architectures that enhanced gas flow, thermal transport, and electromagnetic interactions through geometric effects that amplified physical processes beyond the capabilities of conventional porous materials formed through familiar geological processes. Computer modeling revealed that exotic porosity geometries could create physical property enhancements that exceeded conventional material performance by substantial factors. Isotopic compositions reflecting stellar nucleosynthesis in massive stars created nuclear properties that influence radioactive decay rates, nuclear reaction cross-sections, and cosmic ray interaction probabilities in ways that could modify radiation effects and nuclear heating compared to materials with solar system isotopic ratios. These nuclear property modifications could theoretically create additional energy sources and particle interaction mechanisms that contributed to anomalous dynamical behavior. The recognition that interstellar objects carried materials with properties that reflected their alien formation environments transformed understanding of cosmic visitor dynamics from purely gravitational mechanics to comprehensive materials science challenges that required consideration of exotic physics operating under conditions that remained largely unexplored by terrestrial science. Each interstellar visitor represented a natural laboratory that tested materials science theory under cosmic conditions that exceeded earthly experimental capabilities. Future encounters with additional interstellar objects would provide expanding databases for characterizing the range of material properties that could arise through formation around different stellar types, creating opportunities to develop comprehensive theoretical frameworks for predicting the dynamical behavior of cosmic visitors based on inferred formation conditions and stellar environment characteristics. These comparative studies would gradually reveal the full scope of cosmic materials diversity and its implications for understanding planetary formation throughout the galaxy. The failure of sophisticated orbital prediction algorithms to accurately forecast 3I Atlas's trajectory revealed fundamental limitations in computational models that had been developed exclusively for gravitationally bound solar system objects whose behavior conformed to well-established celestial mechanics principles. These software systems, refined through decades of successful application to planetary motion, asteroid tracking, and comet orbit determination, encountered their first comprehensive failure when confronted with an object whose dynamics were dominated by non-gravitational forces operating through mechanisms that remained poorly understood from theoretical perspectives. Traditional orbital mechanics software relied on mathematical frameworks that treated gravitational forces as the primary determinants of celestial motion, with provisions for small perturbations from radiation pressure, solar wind effects, and outgassing forces calibrated against observations of familiar solar system objects whose behaviors fell within predictable parameter ranges. The magnitude and complexity of non-gravitational effects exhibited by 3I Atlas exceeded the design specifications of these computational models and revealed the inadequacy of perturbation theory approaches when applied to objects with fundamentally different physical properties. Numerical integration algorithms designed for long-term orbital evolution studies faced unprecedented challenges when attempting to model trajectory systems where unknown force components varied unpredictably with time, solar distance, and object orientation in ways that created chaotic sensitivity to initial conditions and parameter uncertainties. Computer simulations that successfully predicted planetary positions centuries into the future failed to maintain accuracy for through-eye atlas beyond periods of weeks or months, highlighting the fundamental differences between gravitational and non-gravitational dominated dynamical systems. Error propagation analysis revealed that small uncertainties in non-gravitational force modeling amplified exponentially over time through chaotic dynamics, creating prediction uncertainty regions that expanded rapidly to encompass vast volumes of space, and made long-term trajectory forecasting essentially impossible using conventional orbital mechanics approaches. These error growth patterns demonstrated that deterministic orbital prediction became meaningless for objects experiencing significant non-gravitational acceleration when force models remained incomplete or inaccurate. The discovery that multiple competing force mechanisms operated simultaneously with comparable magnitudes created computational challenges where traditional perturbation approaches failed, because no single force dominated sufficiently to serve as the primary term in mathematical expansions, requiring development of new theoretical frameworks that could accommodate multiple comparable effects without hierarchical approximation schemes. This theoretical challenge exceeded existing mathematical capabilities and required fundamental advances in celestial mechanics theory. Only took a few weeks of orbital tracking to reveal that existing computational capabilities were inadequate for predicting interstellar object trajectories. Yet developing improved modeling approaches required years of theoretical development and observational constraint that could only be achieved through continued study of additional interstellar visitors. The rapid recognition of computational limitations contrasted with the slow development of theoretical solutions needed to address these fundamental modeling challenges. Parameter estimation procedures designed to determine orbital elements and force model coefficients from observational data encountered convergence difficulties when applied to systems where multiple unknown force mechanisms created mathematical degeneracies and non-unique solutions that prevented reliable parameter determination. Standard least squares fitting algorithms that worked effectively for conventional orbital problems failed to converge or produced parameter estimates with uncertainties that exceeded acceptable margins for trajectory prediction applications. Machine learning approaches offered alternative computational strategies that could potentially identify pattern recognition, relationships between observational data, and trajectory behavior without requiring explicit physical force models. Yet these data-driven methods required extensive training datasets that remained unavailable due to the limited number of interstellar objects detected and characterized with sufficient precision for algorithm development. The promise of artificial intelligence solutions remained unrealized due to insufficient observational training data. The mystery of computational model failure found explanation through recognition that existing software had been optimized for problems where gravitational forces dominated and non-gravitational effects remained small perturbations that could be treated through linearization approximations. While interstellar objects required nonlinear dynamics, approaches where multiple force mechanisms interacted through complex coupling relationships that exceeded the mathematical frameworks implemented in available software systems. Validation procedures for orbital prediction software typically relied on comparison with observational data from objects whose trajectories were well understood through previous studies. Yet interstellar visitors provided no historical database for model validation and created unprecedented situations where software performance could only be assessed through real-time comparison with ongoing observations of unique objects whose behavior patterns remained unknown prior to detection. Computational resource requirements for accurate modeling of interstellar object dynamics exceeded available processing capabilities when attempting to implement detailed physical models that included realistic representations of outgassing, electromagnetic effects, thermal cycling, and structural dynamics through coupled multiphysics simulations that required simultaneous solution of equations governing thermal, mechanical, electromagnetic, and chemical processes operating on different time and length scales. Software architecture limitations in existing orbital mechanics programs created additional obstacles where modular code structures designed for adding small perturbations to gravitational motion could not accommodate the fundamental restructuring required to treat non-gravitational forces as primary rather than secondary effects, necessitating complete software redesign rather than incremental modification of existing computational tools. Real-time trajectory determination requirements for planetary defense applications created operational challenges where software systems needed to provide rapid orbit predictions for potentially hazardous objects. Yet interstellar visitors required extended observation periods and sophisticated force modeling that exceeded the computational time constraints imposed by operational decision-making requirements. These timing conflicts highlighted tensions between scientific accuracy and operational necessity in trajectory prediction applications. International coordination challenges arose when attempting to pool observational data and computational resources from multiple institutions for collaborative modeling efforts. As different organizations employed incompatible software systems, data formats, and theoretical approaches that created technical barriers to effective information sharing and collaborative model development. These coordination difficulties impeded progress toward improved computational capabilities. Quality control procedures for orbital prediction accuracy relied on statistical metrics developed for gravitational dynamics, where prediction errors followed predictable patterns and uncertainty estimates could be calculated through established error propagation methodologies. Yet interstellar objects exhibited error behaviors that defied conventional statistical analysis and required development of new uncertainty quantification approaches that remained largely theoretical rather than implemented in operational software. The implications of computational model failures extended beyond academic questions of orbital mechanics to encompass practical concerns about planetary defense capabilities and space mission planning, where accurate trajectory prediction represented critical requirements for operational decision-making, highlighting the need for fundamental advances in both theoretical understanding and computational implementation of complex dynamical systems dominated by multiple competing force mechanisms. Future software development efforts would require interdisciplinary collaboration between celestial mechanics specialists, materials scientists, plasma physicists, and computer scientists to create comprehensive modeling capabilities that could accommodate the full range of physical processes operating on interstellar objects, representing a significant expansion beyond traditional orbital mechanics toward comprehensive cosmic object dynamics that integrated multiple branches of physics into unified computational frameworks. The technical challenges of precisely tracking 3I Atlas throughout its rapid passage through the solar system pushed astronomical observation capabilities to their absolute limits, as ground-based telescopes and space-based instruments struggled to maintain accurate position measurements of a small, dark object, moving at velocities that created observational conditions unlike anything encountered in routine astronomical monitoring programs. The comet's low albedo, measuring only 4% reflectance of incident sunlight, combined with its modest 2-kilometer dimensions to create a target that remained at the threshold of detectability for most observational facilities, requiring sophisticated image processing techniques and statistical analysis methods to extract reliable astrometric data from noisy observational datasets. Atmospheric turbulence effects that normally represented minor inconveniences for stellar observations became major obstacles when attempting to measure precise positions of rapidly moving objects whose apparent motion across the sky required exposure time short enough to prevent trailing while maintaining sufficient signal strength for accurate centroid determination. Adaptive optic systems designed to correct atmospheric distortions operated with response times optimized for stationary astronomical sources and struggled to maintain stable correction for targets whose positions changed continuously during observation sequences. The rapid angular motion of 3I Atlas across the celestial sphere created additional observational challenges where traditional astrometric techniques required modification to account for object motion during integration periods. As conventional assumption of stationary targets became invalid for objects whose positions changed measurably during typical CCD exposure times, these motion effects necessitated development of specialized observation strategies that balanced exposure duration against motion blur while maintaining photometric signal levels sufficient for reliable detection. Coordinate system transformations between different observational epochs and reference frames introduced systematic errors that accumulated over extended observation campaigns, where multiple observatories contributed data using different instrumental configurations and calibration procedures, creating complex error propagation scenarios where individual measurement uncertainties combined through statistical processes that could amplify small systematic effects into significant trajectory determination errors. The discovery of systematic position errors that varied with object brightness and atmospheric conditions revealed that photometric effects influenced astrometric measurements through mechanisms that remained poorly understood, where variations in apparent magnitude created systematic shifts in measured positions through optical effects that operated differently for point sources compared to slightly extended objects with complex surface brightness distributions. Only took atmospheric seeing variations a few seconds to introduce position measurement, uncertainties that accumulated over hours of observation to create trajectory determination errors, measuring kilometers in the object's predicted location, highlighting the sensitivity of precision astrometry to environmental conditions that remained beyond experimental control. The rapid introduction of measurement errors contrasted with their persistent effects on long-term trajectory predictions, where small observational uncertainties created expanding uncertainty regions over extended time periods. Detector calibration challenges arose when attempting to maintain photometric and astrometric accuracy across observational campaigns spanning months and involving multiple telescopes with different instrumental characteristics. As calibration procedures developed for stellar observations required modification when applied to solar system objects whose spectral characteristics and phase function behaviors differed from stellar calibration sources. These calibration difficulties created systematic errors that varied between different observational facilities and complicated efforts to combine data from multiple sources. The mystery of enhanced measurement noise for rapidly moving targets found explanation through recognition that standard astronomical observation techniques had been optimized for essentially stationary sources where long integration times could average out random noise sources, while fast-moving objects required shorter exposures that reduced signal-to-noise ratios and made precise position measurements increasingly difficult as target motion increased. timing synchronization requirements for coordinated observations between widely separated observatories created technical challenges where precise time coordination became critical for accurately combining observations into coherent trajectory solutions. Yet achieving microsecond-level timing accuracy across global telescope networks required sophisticated atomic clock systems and communication protocols that exceeded the capabilities of many astronomical facilities. Background star field variations introduced additional complications, where the stellar reference frame used for astrometric calibration changed continuously as 3i Atlas moved across different regions of the sky with varying star densities and brightness distributions, creating systematic effects where astrometric accuracy depended on local stellar field characteristics that varied unpredictably throughout the observation campaign. Photometric variability resulting from the object's complex rotation and irregular shape created observational challenges where brightness variations influenced detection probability and measurement accuracy in ways that varied systematically with rotational phase, requiring careful analysis of photometric data to separate intrinsic brightness variations from observational artifacts that could masquerade as genuine physical effects. Spacecraft tracking capabilities provided alternative observational approaches through deep space network facilities designed for interplanetary mission support. Yet these radar systems required significant modifications and coordination efforts to track objects following unpredictable trajectories, rather than the well-defined orbits of mission spacecraft where tracking parameters could be predicted accurately in advance. Data processing algorithms designed for conventional astronomical surveys encountered difficulties when applied to rapidly moving targets that created observational artifacts and false positive detections in automated detection systems optimized for identifying stationary or slowly moving astronomical sources, requiring development of specialized data reduction techniques that could distinguish genuine object detections from systematic artifacts introduced by standard processing procedures. Real-time observation scheduling challenges arose when attempting to coordinate observations between multiple facilities, where unpredictable trajectory behavior made advanced scheduling difficult and required flexible observational programs that could adapt rapidly to changing observational requirements as improved orbit solutions became available through continued tracking efforts. International coordination efforts revealed systematic differences between observational techniques and data reduction procedures employed by different astronomical institutions, creating challenges for combining observations into homogeneous datasets where systematic differences between facilities could introduce biases that exceeded random measurement uncertainties and complicated efforts to achieve optimal trajectory determination accuracy. Quality assessment procedures for evaluating observation reliability required development of new statistical techniques where conventional error analysis methods proved inadequate for handling the complex error characteristics introduced by rapid target motion, atmospheric effects, and systematic instrumental variations that created error patterns unlike those encountered in routine astronomical observation programs. The implications of observational measurement challenges extended beyond technical difficulties in tracking individual objects to encompass fundamental questions about the observational capabilities required for effective monitoring of the interstellar object population and planetary defense applications where rapid and accurate trajectory determination represented critical operational requirements that exceeded current observational infrastructure capabilities. Future observational programs would require significant technological advances in telescope automation, adaptive optic systems, detector technologies, and data processing algorithms to achieve the measurement precision and response times necessary for comprehensive characterization of rapidly moving interstellar visitors whose detection and analysis represented expanding priorities for both scientific research and planetary defense applications requiring advanced observational capabilities. The comprehensive study of 3I Atlas's anomalous motion established fundamental principles for understanding the complex physics governing interstellar objects during their passages through stellar systems, revealing that these cosmic wanderers operate according to dynamical laws that encompass electromagnetic, thermodynamic, and materials science effect far beyond the purely gravitational mechanics that dominate solar system astronomy. Each trajectory deviation, acceleration, anomaly, and behavioral surprise demonstrated that objects forged in alien stellar environments carry within their structure the physical signatures of formation conditions that create exotic responses to stellar radiation, magnetic fields, and gravitational environments encountered during cosmic wandering. The recognition that multiple force mechanisms operated simultaneously with comparable magnitudes transformed interstellar object dynamics from a specialized subset of celestial mechanics into a comprehensive interdisciplinary challenge requiring integration of astrophysics, materials science, plasma physics, and computational mathematics to develop theoretical frameworks capable of predicting and explaining the complex behaviors exhibited by these cosmic visitors. Traditional boundaries between astronomical disciplines dissolved when confronted with objects whose dynamics required simultaneous consideration of gravitational, electromagnetic, thermal, and chemical processes operating through coupled interactions across multiple time and length scales. Future missions designed to intercept and study interstellar objects would benefit enormously from the theoretical foundation established through analysis of 3I Atlas's motion, providing guidance for instrument design, trajectory planning, and data collection strategies that could maximize scientific return from brief encounters with objects whose origins and destinations remained forever beyond direct human exploration. The lessons learned from remote observation of this ancient wanderer would inform spacecraft design decisions and measurement priorities for ambitious missions attempting to rendezvous with cosmic visitors traveling at interstellar velocities. The development of enhanced computational models capable of integrating multiple physical processes into comprehensive dynamical simulations represented one of the most significant advances stimulated by 3I Atlas studies. As traditional orbital mechanics software proved inadequate for handling objects whose motion was dominated by non-gravitational effects, operating through mechanisms that remained poorly understood from theoretical perspectives. These computational advances would benefit not only interstellar object research, but also broader applications in spacecraft trajectory planning, asteroid deflection strategies, and planetary defense initiatives requiring accurate prediction of small body motion under complex force environments. Observational techniques refined through the challenge of tracking 3I Atlas's rapid motion would enhance astronomical capabilities for detecting and characterizing future interstellar visitors, creating improved survey strategies and data processing algorithms that could identify cosmic wanderers earlier in their solar system passages and maintain tracking accuracy throughout their brief periods of observational accessibility. These technical advances would contribute to expanding databases of interstellar object properties and behaviors that could reveal systematic trends and population characteristics. Only took one interstellar visitor to revolutionize understanding of cosmic dynamics and reveal the inadequacy of purely gravitational approaches to celestial mechanics when applied to objects with exotic formation histories and material properties. Yet implementing comprehensive theoretical and computational frameworks would require decades of continued research and technological development stimulated by encounters with additional cosmic wanderers carrying different combinations of physical properties and dynamical behaviors. The implications of 3-eye atlas studies extended beyond academic questions of celestial mechanics to encompass practical applications in planetary defense scenarios, where accurate trajectory prediction for potentially hazardous interstellar objects required comprehensive understanding of non-gravitational force mechanisms that could significantly alter impact probabilities and timing predictions. The inability to predict interstellar object trajectories using conventional methods highlighted critical vulnerabilities in current planetary defense capabilities and emphasized the need for enhanced theoretical understanding and computational modeling capabilities. Materials science research stimulated by analysis of 3-eye atlas's exotic responses to solar system conditions would contribute to advancing understanding of how matter formed under extreme astrophysical conditions exhibits properties that differ systematically from terrestrial and solar system analogues, creating opportunities for developing new materials with enhanced capabilities for space applications, where conventional materials might prove inadequate under cosmic environmental conditions. International collaboration frameworks developed for coordinating 3-eye atlas observations would serve as templates for future interstellar object research campaigns, where global coordination of observational resources, data sharing protocols, and theoretical analysis efforts could maximize scientific return from rare cosmic encounters that provided unique opportunities for studying materials and processes operating under conditions that remained inaccessible to laboratory investigation. The recognition that interstellar objects represented natural laboratories for testing materials, science and physics theories under extreme conditions would stimulate development of new experimental approaches and theoretical frameworks that could bridge the gap between terrestrial laboratory capabilities and cosmic environmental conditions, creating opportunities for advancing fundamental understanding of matter behavior under parameters that exceeded earthly experimental reach. Educational programs inspired by 3 atlas discoveries would introduce new generations of students to the interdisciplinary nature of modern astrophysics and the complex interactions between different branches of physics that must be integrated to understand cosmic phenomena. Preparing future researchers to tackle challenges that required synthesis of knowledge across traditional disciplinary boundaries, the philosophical implications of discovering that cosmic wanderers operated according to physical principles more complex than pure gravitational mechanics reinforced recognition that the universe contained physical processes and material properties that exceeded current theoretical understanding, highlighting the continuing need for observational discovery and theoretical development in advancing human knowledge of cosmic physics and the diversity of matter behavior under extreme conditions. Each future interstellar visitor would add new data points to the emerging picture of cosmic wanderer dynamics and materials properties, gradually building comprehensive databases that could reveal systematic relationships between formation conditions, material properties, and dynamical behaviors that operated throughout the galaxy's diverse stellar formation environments. This accumulating knowledge would eventually enable prediction of interstellar object behavior based on inferred formation conditions and composition estimates derived from remote observations. The transformation of interstellar object research from descriptive astronomy toward predictive physics represented one of the most significant advances stimulated by 3 atlas studies, demonstrating that comprehensive theoretical understanding could emerge from careful analysis of anomalous behaviors that initially defied explanation through conventional approaches. This transformation highlighted the continuing power of observational discovery to drive theoretical advancement and reveal new aspects of physical reality. The enduring legacy of 3I Atlas would extend far beyond its brief passage through human awareness, to encompass fundamental advances in theoretical understanding, computational capabilities, observational techniques, and interdisciplinary collaboration approaches that would influence astronomical research for generations while preparing humanity for future encounters with cosmic wanderers carrying their own unique combinations of exotic physics and alien chemistry toward temporary intersection with human curiosity and scientific capability. As 3 Atlas continues its silent journey toward destinations among distant stars, it carries with it the invisible signatures of human measurement and analysis, electromagnetic echoes of radio telescopes, radar pulses that briefly illuminated its ancient surface, and spectroscopic photons that decoded its chemical secrets. These faint technological whispers accompany the comet towards stellar neighborhoods, where they might theoretically encounter intelligences capable of recognizing evidence of another technological civilization that briefly studied a cosmic wanderer during its passage through alien stellar territory. The cosmic silence that settles over observatories around the world carries with it a profound transformation in humanity's understanding of celestial motion, no longer the elegant simplicity of Newtonian gravity acting alone, but a complex symphony of forces where electromagnetic fields dance with thermal gradients, where ancient magnetic memories interact with solar wind plasma, where the very structure of matter forged in alien stellar furnaces responds to solar system conditions through mechanisms that transcend terrestrial physics experience. The departure of 3I Atlas leaves behind not just expanded knowledge but fundamental questions about the nature of cosmic dynamics and the exotic behaviors that emerge when materials from distant stellar neighborhoods encounter environments shaped by different stellar evolution histories. In the growing quiet of tracking stations no longer able to detect the fading object, scientists compile the final measurements that chronicle months of orbital surprises and theoretical revelations. Each data point represents a glimpse into physics, operating under conditions that bridge the gap between laboratory science and cosmic reality, where forces measured in fractions of percent accumulate over astronomical distances to redirect cosmic trajectories toward destinations that will forever remain beyond human verification. The patient accumulation of these microscopic measurements reveals the profound sensitivity of cosmic motion to physical processes that operate through mechanisms barely detectable by terrestrial instruments. The mathematical equations that now describe 3I Atlas's motion encompass electromagnetic theory, materials science, thermodynamics, and plasma physics in addition to classical gravitational mechanics, a theoretical complexity that reflects the multifaceted nature of cosmic physics, operating on objects whose formation histories encompass stellar environments unknown to solar system experience. These expanded mathematical frameworks represent humanity's first comprehensive attempt to describe the motion of matter that carries within its structure the physical signatures of alien stellar chemistry and exotic formation conditions. Somewhere in the deep future, when 3I Atlas approaches its next stellar encounter after tens of thousands of years of cosmic wandering, the forces that shaped its anomalous motion through the solar system will continue operating according to physical principles that remain independent of human observation or theoretical understanding. The electromagnetic fields embedded in its metallic components, the thermal expansion coefficients of its exotic minerals, the sublimation behaviors of its alien eases all will respond to foreign stellar radiation according to the same physical laws that created measurement challenges and theoretical revelations during its brief intersection with human awareness. The recognition that interstellar objects operate according to physical principles more complex than pure gravitational mechanics transforms understanding of cosmic wandering from simple Keplerian orbital motion to comprehensive materials. Physics challenges where the formation environment of objects determines their dynamical behavior during subsequent cosmic evolution. Each cosmic wanderer becomes a natural experiment in physics, operating under conditions that remain forever inaccessible to direct laboratory investigation, carrying within its structure information about stellar formation processes that operated under physical parameters that exceed terrestrial experimental capabilities. Only took a few months of intensive observation to reveal that the universe operates according to physical principles more complex and interdisciplinary than classical celestial mechanics had encompassed. Yet implementing comprehensive theoretical frameworks for predicting cosmic wanderer behavior will require decades of continued research stimulated by encounters with additional visitors carrying different combinations of exotic physics and alien chemistry. The rapid recognition of theoretical inadequacy contrasts with the slow development of enhanced understanding needed to address fundamental gaps in cosmic physics knowledge. The technological advances stimulated by 3 Atlas studies improved computational algorithms, enhanced observational techniques. Sophisticated error analysis methods will benefit astronomical research far beyond interstellar object investigations, contributing to advancing capabilities for spacecraft tracking, asteroid deflection planning, and planetary defense initiatives requiring accurate prediction of small body motion under complex force environments. These technological legacies ensure that the brief encounter with one cosmic wanderer will continue influencing astronomical capabilities for generations. The departure of 3I Atlas toward the constellation Telescopium carries these lessons into the cosmic future, where they will remain forever associated with its continuing journey through interstellar space. The electromagnetic signatures of human radio telescopes embedded in its coma during months of intensive study travel outward as inadvertent messages toward destinations where they might theoretically encounter intelligences capable of recognizing evidence of technological civilization that develop the capability to analyze cosmic visitors during their passage through alien stellar systems. Future encounters with interstellar objects will build upon the theoretical foundation established through 3I Atlas studies, gradually expanding understanding of cosmic materials, diversity, and the range of dynamical behaviors that emerge when matter formed under different stellar conditions encounters solar system environments. Each new visitor will test and refine theoretical frameworks while revealing additional aspects of cosmic physics operating under conditions that remain unique to each formation environment. The philosophical transformation wrought by recognizing that cosmic motion encompasses physics far beyond gravitational mechanics reinforces humanity's position as participants in a universe whose complexity continues expanding beyond current theoretical understanding. The discovery that ancient wanderers carry within their structure physical signatures of alien stellar chemistry and exotic formation conditions emphasizes the continuing need for observational discovery and theoretical development in advancing knowledge of cosmic processes operating throughout galactic stellar populations. As measurement uncertainties expand and tracking capabilities fade beyond instrumental limits, 3I Atlas transitions from direct observational study to theoretical modeling and computational simulation, where the lessons learned from its anomalous motion will inform predictions about future interstellar visitors and guide development of enhanced capabilities for cosmic wanderer detection and analysis. The transformation from observed object to theoretical foundation ensures that its contribution to cosmic physics understanding will persist long after its physical presence disappears beyond observational reach. The enduring mystery of its ultimate destination involves probability calculations that encompass billions of years of galactic evolution and gravitational encounters that could eventually deliver its exotic materials to planetary surfaces throughout stellar neighborhoods where its alien chemistry might contribute to local chemical evolution. These cosmic wandering scenarios operate according to statistical mechanics that make individual outcomes unpredictable, while ensuring that eventually, somewhere, the materials forged around distant massive stars will encounter conditions that test their potential for contributing to cosmic chemical complexity. In the growing darkness beyond the outer solar system, 3i Atlas continues its patient journey according to the complex physics revealed through human observation, electromagnetic forces and thermal expansion, magnetic interactions and sublimation instabilities, gravitational asymmetries and materials properties that reflect formation under stellar conditions unknown to solar system experience. The Cosmic Wanderer carries forward the continuing story of matter circulation between stellar systems, distributing the physical signatures of alien stellar chemistry throughout galactic neighborhoods according to dynamical laws that encompass the full complexity of cosmic physics. The eternal circulation continues wandering seeds carrying exotic physics toward future encounters that will test cosmic materials, diversity against environmental conditions shaped by different stellar evolution histories, each intersection providing opportunities for cosmic physics experiments that operate over timescales spanning millions of years and distances measured in light years. Sleep well, Cosmic Wanderer. Sleep well, Physics Laboratory. Sleep well, ancient messenger carrying alien materials toward unknown destinations where exotic chemistry meets possibility.